right, good morning, everybody. Thanks. Okay, so I posted this last time about moving office hours from Wednesday to Friday at the same time. So there's been an overwhelming response at a rate of 21%. That I would say is not representative. I do appreciate those who have already logged your answers. As I've said before, this is motivated by the fact that homework's due on Sunday, so we want to have a TA available on Friday later in the week so that it gives you more time to look at the homework and come to office hours, or at least reach out to the TA that has office hours on Friday so that we can provide additional resources, or at least the same resource, just at a later time. So please, please log in your answers. This poll will close tonight. So obviously you don't have to do it now. It remains open, so we get your feedback on this. Okay. And you may be more excited, probably more earnest to know about the results of exam 1. Well, apparently, I wrote this announcement last night, but this morning I did get an email from exam scoring, and so your exams just got back. So I haven't updated anything yet on Carmen because I just received the email with your scores. That being said, there actually is an individual who hasn't not taken it yet due to some dire illness, and so I will refrain from actually releasing any scores or even an average so that we're all on the same page and everybody takes the exam with the same amount of information, which is really nothing, so as to not skew their performance one way or another. Okay. I also want to note that your homework 4 has a question, actually a tutorial on plastic deformation. It goes into depth about the slip direction and slip planes. Now, we sort of discussed that, but I didn't go into detail about the more quantitative aspects of that, so I've actually reassigned. So there was like maybe 3 people that have completed this question so far out of 181. So if you've done that, then great, thank you. But for the overwhelming majority of you that have not attempted the question or completed it, I've actually set the question value to 0 points so that you get a chance to practice, but that way, you know, it doesn't actually count towards your homework score because it goes into greater detail. I haven't had a chance to go into the great detail in class, and unfortunately, I won't be able to for the sake of keeping pace with this class schedule. So I've adjusted the score for that reason. So you're welcome to practice and really go into depth about slip, but it won't be counted against you, okay, if you don't. I also want to note on your homework 4, please pay attention to the logarithmic axes that are both the x and the y axes, and I think this could be a point where you may or may not get tripped up, so I just want to highlight that, okay? So keep that in mind when you're doing the homework, because what's in your book, it says log of, it's a question regarding stress and the crack length, and in your book, it's very schematic. It's figures 8.6. It's quite schematic. It just says log, and it looks like it's a curvature, but if you actually go through the problem and you plug log, log, you'll see what the answer obviously is. So that's a very big hint towards, you know, you're trying to comprehend that question. Also, we're about, you know, approaching the midway point. So I will issue out a mid-semester Qualtrics anonymous survey to get your feedback on the pace of the course, what you like about the course so we can continue that, what you think could be constructively changed, emphasis on the constructive. We're all humans, and so I do value your feedback in terms of the organization of the class, homework pacing, homework level, type of lecture styles. I try to balance between conceptual type of lecture and also just, you know, the plug and chug, going through and crunching the numbers together. But if you feel like, you know, the course could go more in a direction of more quantitative analysis versus the conceptual or vice versa, then please let me know, and I will adjust and take your opinions into account. There are some things that are not constructive, so you're very welcome to voice your opinions about the textbook, about mastering engineering, all of that. So currently, the book is the textbook. I have many opinions myself about it, and so we are addressing that. But if there's an overwhelming response about what we can do constructively about the textbook or something like that, we will try to address it as a department as well. Okay, let's see what else. Yeah, so office hours response rate, let's get that up so that it's a meaningful statistical number. And the last thing is top hat synchronization. We've tried to synchronize your top hat in-class participation grade as well as your recitation participation grade. Obviously, the numbers are a little bit skewed because you're not a part of the other recitations. I think this is not a good way to continue. We've been talking with Top Hat. There has not been a viable working solution. And so I'm going to depart from the way I've been synchronizing Top Hat with Carmen so that the first number you see is not something ridiculously low, okay? So that means we're reorganizing the way Top Hat is synchronized. So for now, I'm going to take away all of the Top Hat synchronization. So the only things that will be reflected in your Carmen score is really your homework assignments and eventually your exam 1. All of your participation grade will still stay in Top Hat and be recorded as so. Nothing is going away. It's just the synchronization will change because the current solution is not a good one. So, okay. I think that takes care of a lot of the housekeeping issues. Any questions or anything that I'd missed so far, logistically? Okay. Well, that will then get us back on track to wrapping up mechanical properties and behavior, chapter 6. If there's time, we'll start on chapter 8, failure analysis and fatigue. We should be wrapping up failure analysis and fatigue come Wednesday. So the start of your lecture series, expert lecture series, will start on Friday. And so these expert lectures mainly come from the materials department. We're trying to get some more from mechanical and also some from plastic surgery and more on the biomedical side, given the diversity of your majors in this class. And these people, these are experts, hence the expert lecturer, and they all do work around these types of topics. So Professor Jennifer Locke does a lot of really great work on corrosion analysis and also failure analysis, which is why she's coming up first after creep and the discussion of fracture toughness and all of that. She does some very fun things in terms of breaking things. She works at a much more macroscopic level than I do. So it'll be really fun to ask her questions about how she breaks things and corrodes things intentionally and also tests samples at an accelerated pace. So anyway, so we'll wrap that up so that you're prepared with the fundamentals before she comes in. Okay, let's see. Okay, so let's back up a little bit. Okay, where did we leave off? Right. We left off at the discussion of creep and stress relaxation. So just to remind you, creep is a static load. Okay, you're applying some load in tension, and now you're just leaving it there and looking at the strain over time. Okay, so you're looking at epsilon as a function of time, and this will change for metals. This will also change for polymers. Okay, and this is particularly important because once you make a material, when it's in service over time, the properties, the mechanical behavior will change, and thus you need to predict what this change will be so that we don't have catastrophic failures like, things not working properly in structural components. If you're also dealing with strain that's changing over time, you're also concerned about strain changing over time as a function of temperature. A lot of these materials that we have that are thermally activated becomes a concern when it's about 40% of the melting point, which for some materials is quite high, some materials is quite low. So a good example would be aluminum. Aluminum melts at 600 C. So 40% of that, is a relatively low temperature when it comes to dealing with metals. Okay, when you're dealing with other elements like cerium or something like that, obviously the melting point is higher. So there, we're talking about 700-800 degrees C. Okay, so that's less of an issue. But there are applications like I mentioned previously a number of times, right? Engine blades. There are some serious concerns when you're operating your engine blade in any aircraft. It's really high, strain over time at an elevated temperature. There, you really want to be able to predict when this part is going to fail on you. Any part of a chassis, right? Especially near the engine, there's going to be elevated temperature. If you live in Phoenix, melting of aluminum could be also an issue at times when it's a really, really hot day. So these are the reasons why we concern ourselves with creep mechanism. If you're launching a component into space and you're SpaceX and you want to reuse your launcher, say, which is what they want to do. They want to reuse their launch because obviously they want to maximize profit. If they can make a part once and then reuse it and test it, non-invasively to make sure it can be reused again, you want to make sure that you haven't experienced creep, okay? So let's review this because I discussed this at the end of class last time. So I just want to review it since it's been quite a number of days, right? So you have three phases of creep. First, you have the elastic component there. So let's see, yeah. So I typed it up so that you don't have to experience my handwriting, especially with long sentences. Okay, so you have three parts of creep: primary creep, secondary creep, and tertiary creep. The part that we're talking about today is going to be secondary creep, where it's steady state. The creep rate is not changing. So rate indicates that something is changing as a function of time, right? So here in primary creep, usually you have, excuse me, sorry, my throat is experiencing something today. So in primary creep, you have this instantaneous, section right here, and then you have strain hardening. That's instantaneous change. You could see the strain just jumping up. That's your primary region. Then all of the secondary region are in here in these dashed lines. And then you have tertiary creep. That's a more complex mechanism, but essentially what you think is happening, right? There's been necking, and so your cross-sectional area is actually decreasing, so your strain rate actually increases over time. So we'll concern ourselves with this region right here. And of course, you could also have no creep. If you're if your load is well below that causes creep, or your temperature is well below that of 40% of a material's melting point, you don't really have to concern yourself with this thermally activated mechanism, okay? It's a diffusion-based mechanism. You don't have to concern yourself about that as an engineer. Okay. So how do we think about the creep rate? We have a relationship between the activation energy of creep, QC. So this is a familiar form of something that's thermally activated and its rate, right? Before we saw vacancy diffusion, self-interstitial diffusion. We saw diffusion of one element into another. So that's just diffusion. We looked at the diffusion coefficients. Now we're talking about steady state, this epsilon dot steady state creep rate. That's related to the activation energy QC divided by the familiar gas constant and temperature, okay? These are materials parameters that you're either given because you've tabulated this sort of information. And so you could calculate the power law, the exponent of the stress that's applied. And so you know if you apply a certain stress, sigma, you know, what the strain rate is going to be. This is particularly useful when you're trying to accelerate failure and fatigue, actually. So if you know at a certain temperature with an applied load what your steady state creep rate is going to be, you could sort of extrapolate that to what happens when I experience creep at a higher temperature or for a longer period of time. So failure analysis, accelerated failure analysis is quite useful when you know these things. So, excuse me. I apologize if I'm clearing my throat a lot. Okay. So you may or may not have seen this type of curve before. I know it's given here as a top hat, but I actually want to just discuss it in great detail because your book has it flipped. So the figure that's in your book is stress as a function of the time, or strain as a function of time. Whereas here, the x-axis is shown as the rate. So it's just 1 over the time. So it's inverse time. So it's just the inverse of what's in your book. So thus, the figures that you'll see will be a little bit flipped. But this is the typical figure that you'll see when you do these types of failure analysis. You see some applied stress as a function of steady state creep. So you see here on the left side is a small number, right? So I'll redraw it because it's a little bit blurry. And then here on the right side is a larger steady state creep rate. So your rate is higher on the right and it's lower on the left. So if you're looking at these three curves, this is the same material. You're tracking the strain rate. You're at different temperatures. So A is at 1 temperature, B is at a 2nd temperature, and C is at a 3rd temperature. So every single data point that's collected along these lines is at the same temperature, okay? So then, and I emphasize that because it's quite different from the type of diffusion plots that you've seen. So I just want to emphasize, you know, the takeaway here, the difference. So if they're at the same temperature, one has to ask, okay, if I see something that's up here, if you need to apply a high stress to cause the same amount of steady state creep rate going from low to high here, that's going to be at a lower temperature than something that's down here. Okay, so something that's right here. So what that's saying is at a higher temperature, your applied stress doesn't have to be that much to induce this sort of steady state creep for you to see the steady state creep rate. So you could see it going from a small number to a very high number at very low applied stress. Okay, and so you can relate that back to the steady state creep rate equation that we talked about before, and you could get the power law exponent when you take the log of both sides. Okay, so your slope is actually going to be 1 over n. Okay.
So stress is lowest at the highest temperature?
The applied stress into induced creep rate, steady state creep rate. Yeah, so it's not so obvious the very first time you see this, or even just staring at it for a while.
If the temperature was higher, you wouldn't need as much stress to get it to creep.
Exactly, yeah. So the highest temperature is actually the lowest applied. I'm sorry?
You just got to pay attention to what the graph is comparing.
Yeah, so that's something I want to highlight. You'll also typically see these types of plots where stress in megapascals on the left and stress in units of PSI or KSI, 1,000 PSI, is on the right. Typically, I'd say, you know, if you had to pick one unit to really be familiar with, go with MPa. Okay. So there are a number of ways to, yeah,
Just a quick question.
yeah.
What is case of C and then sigma to the n? Is n just is a variable or is n significant?
N is a variable that changes with material. So if you're working with creep of aluminum versus creep of steel versus creep of something else, that will definitely change. And you have to back that out based on the experiment that you do. So if you can apply a load and then you just measure that strain at different temperatures, you can produce these types of plots. And so you basically have to produce these types of plots because, as you can see, it's a fitting parameter. N is a fitting parameter. You have to back that out. And then Kc is also a materials property that relates your applied stress to the steady state creep rate. And so you have to back that out as well. Now, there are databases. If you work with a typical material, if you're engineering into some component or device, you'll pick something that's been well studied, has all the ASTM values already, then that number will be available for you. If you don't, let's say you're making a new material, this is something that you're going to have to just tabulate and measure and then report, when you're trying to sell it or something like that. So with any sort of Arrhenius type thermally activated equations that you see like this with diffusion or here the steady state creep rate, you can back out the activation energy if you don't know it, and that's something we practice together in class when you're given, when you're given several variables that you know, but you don't know the activation energy. Okay, so that's something you can back out in a similar way. Another way is this example here that I'll talk about. So if you're given steady state creep rate for some alloy, some material taken at one particular temperature, here I give an example, 473K. Okay? If you know the epsilon value, the creep rate, and you know the activation energy, here it's 140,000 joules per mole, you can compute the steady state creep rate at a higher temperature or even a lower temperature, right, and another stress level. So this is what I mean by you can extrapolate this information so that you can test at a lower temperature to guess at a higher temperature what's going to happen. Will it fail, more rapidly? So if you're given something like this, where here you have a rate per hour, and here's the applied stress, you can calculate the new, excuse me, you can calculate the new steady state creep rate at an elevated temperature. So let's look at what we're given. So I've just rewritten the example here with all the values. So let's write out what we do have. As Zachary asked, how do you know what N is? N is the power law exponent, so it's particular to the material, so we have to go find N. So we write out what we know. We know that the steady state creep rate is given as so, and I've taken the log of both sides, okay, because now we're going to have to back out what N is. So here you can see, okay, well, log of the rate that we're given at a certain temperature and applied stress of 55 megapascal. We don't know what the materials, this proportional factor is. We don't know what that is yet, so we just write the log of that. We also know that at another value of applied stress, we get this creep rate, okay? And still, we don't know what the material is. Here, it still should be 473.
Shouldn't it be 523?
No. No. So we're at the same temperature, okay?
Oh.
We're at the same temperature, two different applied stress. Okay. So for one temperature, this is what we know so far. We don't know what the materials parameter, the exponent, is. So you have N that you don't know, and you have this material proportional constant that you also don't know yet. So let's solve for N first. So if we, sorry. The blocking is a little bit uneven. But if we combine and say, okay, well, if this is a constant and this is a constant, these two equations can be equal to each other. Okay, so I put this, I move this over here, so I have this is equal to the other applied stress. So all I did was just put the two equations equal to each other. Yes, Kevin?
Where did you get the 2.5 times 10 to the negative third from?
That's given.
My mistake.
That's given. I just didn't copy it over. So you have to know these things. You have to be, these values have to be tabulated already for one temperature, okay? Okay, so if you know that, you put the two equations together. Now, n is the only unknown in this set of equations. So then if you move the n over here and then these values to the right, you can solve for what n is. N times these log of 55 plus log of 69, sorry, the negative of log of 55, log of 69, you get this. And so n is then going to be 9.98. So that's what we just solved, okay? So far, I've just manipulated the rate equation. That's all I've done, okay? So then we have to plug it back in to calculate what the materials parameter is, Kc. So if you solve for Kc, we know at an applied stress of 55 megapascal, the power law exponent is 9.98 for what we just solved. We know the activation energy for creep at 473 Kelvin is 140,000 joules per mole. The steady state creep rate is 2.5 times 10 to the minus 3 per hour. That was what we were given. So then we can calculate for Kc. And if we assume the mechanism of creep at 250C or 523K, what we're calculating for, if we assume the same mechanism, which we do often, we can calculate the new steady state creep rate is 1.9 times 10 to the negative 1 hour per percent per hour. So that's the strain per hour. Is that, oh, actually, I think it should be negative 2. I need to check my exponent on this. Let me check and get back to you as I'm remembering. Actually, I don't even have to check it. Let's do it together. If ever in doubt. Okay, let's see. Let me get my values in place here. One moment. Let's see. Okay. This is being blocked. So let's see. It was Kc is, what was it again? Somebody just shouted out at me. Okay. 3.09 times 10 to the negative fifth times what was a 55 to 9.98 times negative 140,000 joules per mole divided by gas constant times 523, the new temperature. I forgot the negative. Thank you. Wow, even Wolfram is taking a long time. Let me see. So it should be, well, it should be, you know it should be a lower number. The creep rate should be a lower number because you're at a higher temperature, larger number. So actually, I must be missing something here. 3.09 times 10 to, did I miss a? Oh, thank you. Thank you very much. Wrong applied stress. Oh, so it's 1.9 times 10 to minus 2. The notes has minus 1, I think, or my slides current. No, it says 48. So I caught that typo and updated it. Yeah. Yeah. Okay, so this should be -2 according to Wolfram. Okay, so that should be a -2 per hour. That's the unit. Because strain is a percentage or a fraction, but it is unitless, okay? Okay, so that's how one would tackle this type of question. The other type of approach is if you don't know the activation energy and you have a set of equations, just like you did with diffusion, with the diffusion coefficient or the diffusion rate itself, you can back out what Q is. Okay, here you're given Q, but if you're at 2 different temperatures and you don't know what Q is, same approach as diffusion. Okay, yeah. Okay. You can always come up after class. Okay, so that is creep in a nutshell. Now let's talk about creep and also stress relaxation, because once you have these things in tension and there's movement in materials such as polymers, you can also have stress relaxation. With some applied stress, materials can actually try to go back to their original structure. And we'll talk about also how do we discuss structure and movement of these atoms within these materials, within the polymers, aka viscosity. Okay, so you've seen this plot before where we talk about specific volume, so that's the y-axis, as a function of temperature. We talked about how the crystal structure, atoms within the crystal structure can rearrange when they're at elevated temperature and then when you cool them down, right? When you cool them down from a liquid state to a solid state. There, typically, we just go through the melting temperature. So for metals, they're liquid, the atoms are all floating around, and then they go into this crystalline structure, and then we have a solid that we can talk about and that we can deal with. In glasses and also polymers, there's a temperature called the glass transition temperature, TG. And here the volume change is different. The mechanical behavior is also different above TG and below TG. So TG is a glass transition temperature where your material behaves more like, so here it's rigid. So you have some elastic response in terms of the mechanical behavior in a material. Here you have a viscous or liquid-like behavior. In some polymers, there isn't really a temperature of melting. The TG just sort of just blends into the melting point, and then you have decomposition. You're basically, if you're just increasing the temperature, some polymers will just sort of, the structure will wiggle around a little bit, and then you have decomposition. And so melting temperature of polymers is something that's much more nuanced than just saying, okay, temperature melt. Because when the structure becomes so disordered, what is the formalism of a disordered state of material? What is the crystal structure? How do you define this change? So sometimes it's not so clear-cut in terms of polymers. In materials like metals and such, it's very obvious. It's a liquid or it's in a solid form. Okay, so there we don't really talk about a TG because, as you can see, it's just a very rapid change in volume as a function of temperature. Okay. So we discuss these terms and these concepts because it's quite important when we talk about polymers, elastomers, right? When we talk about materials such as the rubber that's in your tires, they're heavily cross-linked, and so their rigidity is something that's important to us because that is affected by highly affected by temperature. So when you're servicing when your tire is in service, on a very cold day versus on a very hot day, you want to make sure that you know how your tire behaves across a huge temperature range. And then when it's stressed, it's going to want to relax away from the stress. So if you give it enough time, there will be stress relaxation. So we discuss, what is that stress relaxation time, which is tau. So here you see another type of equation that looks eerily like the Arrhenius equation. And so here we say, okay, if you apply some stress on your polymer, and then it's going to want to relax to its original structure, to decrease this stress, it's going to go through what's called a viscous flow. So it's going to, that mechanism is going to allow your material to relax from a stress state. And the amount of time that it takes to go back to the original stress that it had is this tau. And it's related to the activation energy that caused it to begin with. And of course, it depends on temperature as well. And we sort of say the relaxation time is 0.37 that of the original applied stress. So that coincidentally is 1 over E. So we basically have, you know, something that decays exponentially like this. Okay, so this is 1 over E. So we say, okay, how long does it take for, you know, the stress to come down to this point, which happens to be 0.37. That's of the original applied stress. That's all that it is. And you'll notice a lot of times that these rates are sort of determined, or these values are determined because it's of the natural log. So then maybe you step back philosophically and say, what makes E the natural log? What's so special about E? Right, because it's quite applicable in diffusion mechanisms, right? It's quite applicable in the way population growth is calculated. It's applicable in the way we model how plants grow. It's quite natural. But what is a natural process? I don't know if any of you have ever sat back and said, what is so special about E? What's so natural about E? Okay, I'll leave you to that philosophical discussion for yourself. I have many opinions on that. But anyway, okay, so stress relaxation. When the material is experiencing stress, it goes through a number of stages, right? So first you have some rigid structure. So if you look at the modulus of elasticity, you'll see, okay, at high elastic modulus, the material is quite rigid. This region right here, actually, I should be, yeah. This region right here, your polymer is quite rigid, okay? If it has high elastic modulus, if you remember from your stress strain curve, it looks something like this, okay? This is very high elastic modulus. I'll show that in red, versus something that looks like this. So you could see the modulus is not that high. Okay, that's what we're talking about when we're talking about modulus of elasticity on a log scale. So it goes from quite rigid, and as the structure relaxes, it goes through a leathery phase and then a rubbery phase. Oh, sorry. Oh, dear. Okay. I did not mean to do that. So let's. Oh, it's one of those. Okay. Sorry, it should be down here. And then a rubbery phase. And so this particular region is important because this is what you experience in most everyday life with polymers, right? Rubber bands. This is the region that you care about. You know, how much is a rubber band going to stretch? And then viscous flow. There's very low modulus of elasticity. And this rubbery region, as you can see, can extend for over a wide range of temperatures, okay? And so when you're thinking about designing materials and selecting materials with different TGs and also how separated it is from the melting point or the decomposition temperature of a polymer, that tells you a lot of information about how elastic, what kind of elastomer your polymer is going to be. We also talked about percent crystallinity. So you have 100% crystalline polymer versus 100% amorphous polymer. They're going to behave quite differently. So if you have crystalline polyethylene versus, say, 100% amorphous polyethylene or 100% polystyrene, right? Your styrofoam, that's 100% amorphous. They'll behave differently for the same type of material with different crystallinity. And so if you're trying to engineer something, a material, a polymer that's very strong or I should say, that's very stiff, then you're going to want higher crystallinity. If you want it to have to be more rubbery, then you're going to want something that's somewhere in between. As you can see here, the region of what's rubbery is not that much. But if you have some percentage of, here it's 50% amorphous, 50% crystalline, then you can extend the rubbery region a little bit more. Okay. So, slightly different than how we talk about mechanical properties when we talk about mechanical properties of metals and ceramics. You wouldn't have any of this in ceramics. Okay. So, let me come back to this summary because I want to move on to classification of polymers. We'll go into greater detail when we talk about polymers in Chapter 12, but I just want to introduce the topic of thermoplastics and thermosets. So here, when we talk about thermoplastics, these are the things you think about when you think about recycling polymers. They're ductile materials. There's very little cross-linking, whereas thermosets have heavy amounts of cross-linking. So those are your rubber tires. They're heavily cross-linked with sulfur-sulfur bonds in your rubber. So that's vulcanization. Okay, they're usually hard and very brittle. So you could see the mechanical properties of these two classes of polymers are quite different. So when we talk about polyethylene terephthalate, PET, when we talk about your PVC pipes, high density and low density polyethylene, your water bottles, your milk jugs, things like that, that's your Heinz ketchup bottles, those are your thermoplastics. If you want things that are, that you've cured and they're heavily cross-linked, that's your rubber tires and your epoxies and such. So if you've ever if you've ever bought epoxy from a hardware store to glue something back together, usually you pump it out of 2 tubes and then you mix it, you're cross-linking and curing your polymers, okay? Okay, so what exactly is happening to the structure of polymers when it's undergoing some applied stress? So here you could see the different stages where if you're just pulling, you're applying some stress and there's some strain, there's some percent elongation, okay? What's happening is that now the chains in a semi-crystalline polymers, these amorphous chains are starting to line up. And so that's what you see here. So they go from being quite amorphous and bundled up to lengthening and starting to sort of line up with each other. Okay, these are the crystalline components right here. They're already lined up. And then as you go beyond the point of elastic deformation, now your material is deforming in a way where the crystalline chains are also coming apart and your amorphous regions are becoming even more elongated. And you could see that here in the cross-sectional areas as well. You could see it being elongated. And finally, near fracture, you are basically now starting to pull apart the carbon-carbon bond. So here you were just changing the secondary type bonding, but at fracture, you're basically just ripping apart the primary carbon-carbon bond. You are just breaking apart your material. Your secondary bonding has been long gone. Okay, and actually what happens right at fracture, what really happens, this mechanism is still being studied today on a material that is quite mature, which is polyethylene. One of the reasons why that is because the ways that we have, like X-ray scattering, X-ray diffraction, the techniques that we have to actually probe these types of mechanisms, they have a certain resolution limit. And thus we can say something about what we think is happening, but of course, materials aren't perfect, and so there's still debate. Now, a healthy debate, not like, is it or is it not, but really what is the nuanced mechanism is the debate that's still going on today, and it's a huge area of research. But this is the generally agreed upon mechanism for polymer elongation when it's under tension. So now let's talk about thermosets. As I've said, they're heavily cross-linked and they're brittle, right? They're hard and they're stiff and they're brittle. So what happens there is if it's heavily cross-linked like this, so if this is your primary bond and these are your sulfur-sulfur cross-linked bonds, what essentially is happening is that you're starting to break those bonds already. And so here, there isn't a whole lot of plastic deformation that one would experience in a typical stress strain curve. So you could see it just leads straight to brittle failure. There's really no elongation. On the flip side, you can have elastomers like your rubber bands where it's highly amorphous like this, and then it becomes straightened like this. Okay. So I've noticed that there are slides 103 to 112 or so. Disregard those slides. They were supposed to have been deleted. As you could see, they are blank sometimes, so those should have been deleted, and they should not have been uploaded. So please disregard those slides. Given the time that we have, I just want to go into the discussion of fracture toughness a little bit. Let me see. This was downloaded. Just to get us started, I know we have only a few minutes left, but let's get started so that we cover some ground on failure, mechanical failure analysis and fatigue. Okay, so we talked a lot about the mechanical properties of materials, when materials will fracture. Now we want to talk about the specific mechanism of which they fracture or rupture. So we'll talk a lot about how ceramics fracture, how metals fracture, and also what happens there. All right, let me jump ahead to this example because it will be a good place to stop after this. So if you work with metals, right, we said metals are ductile. We said that they can withstand some strain before fracture, unlike ceramics where you have elastic deformation and then fracture, okay? There are certain situations, such as at very low temperatures, where your metal is quite brittle and behaves like a ceramic. This is a situation that you want to avoid at all costs because it will be a disastrous, catastrophic, very fast fracture. And so we have two history examples in history where this has happened because we didn't know better, and now we do know better. One example is the Titanic. The other example is the World War II Liberty ships. Both of these types of ships basically just cracked because they were stored at very low, cold temperatures. Liberty ships are stored in the New England area where temperatures are quite low often. And the Titanic, of course, was going through the Atlantic, and of course it hit an iceberg, but on top of that, it was in a very cold ocean. And why the temperature matters is because of what's called the ductile to brittle transition. So what we talked about before was metals are ductile, right? So they can withstand very high, okay, you'll have to follow my mouse. They can withstand a lot of energy, impact energy, okay? And brittle materials like ceramics cannot. They cannot absorb that much energy before fracture. The temperature of which it matters to metals is this ductile to brittle transition temperature. So what you want to engineer is a metal that it has a very low ductile to brittle transition temperature so that when you're servicing this metal, when this is in service, and highly important for steels because iron is BCC, it goes from being brittle to ductile. So you want to be in this ductile regime. The Titanic and the Liberty ships were not, And so their ductile to brittle transition temperature of the metal that they were using for the whole of the ships and other parts of the ship had a ductile to brittle transition temperature that was about room temperature. So you could see, being in a cold ocean, they were sort of here-ish, right? The operating surface is here, which means the material, the metal, is actually quite brittle. So upon impact into an iceberg, say, it's just going to fracture. Okay? So that's an important piece of dealing with metals and fracture. We'll pick up on this come next lecture, and I'll post your scores by then as well.